Hello, my name is Luca DeCicco.
Hi, I'm Leah Jackson,
Hi, I'm Katie Weatherwax.
and today we're presenting a sensor system for biomolecule detection using flexible sensor array.
Our mentor is Gunhee Kim, and our faculty advisor is Dr. Bernard Kippelen. So today, most medical analyses require invasive and expensive blood tests, and patients generally need to know what they're looking for these tests to be approved at all. Improving continuous monitoring with wearable sensors can fix this problem. One example is glucose monitoring for patients with diabetes. Instead of checking their blood sugar levels every so often, a patient with a wearable sensor could be alerted every time those levels fall outside of a certain range. Unfortunately, these types of biosensors are expensive and not very comfortable. As such, they're not commonly used. With organic field effect transistors, or OFETs, this could change. The semiconducting layer in an OFET reacts to organic environmental factors such as pH. In this way, they can be used as a sensor for medical diagnostics. In addition, they are relatively cheap to produce in bulk, use very little power, and unlike other transistors, they can be flexible. This means that OFETs can be comfortable as well as functional. The challenge for using OFETs in this way is that their electrical characteristics degrade when in direct contact with aqueous environments.
Okay, so what exactly is an OFET? Fully known as an organic field effect transistor, these utilize the principles of semiconductors and are composed of a source, drain, and gate. Charge travels from the source to a drain along a pathway through the semiconductor. The amount that passes through is based on the amount of voltage detected at the gate. The presence of biomolecules can be detected by an electric charge on the gate of the OFET. So by applying a voltage to the source and drain terminals on the OFET, the conductivity of the semiconductor layer is changed. The amount of current detected is used to determine the molecule type and concentration. To fabricate OFETs, thermal evaporation will be used to deposit source, drain, and gate. Also, gate insulators will be deposited using atomic layer deposition and organic detection layer. Will also be deposited using spin coating. All OFETs are built of three main layers. There's a substrate, the foundation for the rest of the transistor structure. The substrate is always the bottommost layer of the OFET. Then there's the insulating layer and the semiconducting layer. How these layers are ordered in the positions of the source, gate, and drain determines many of the device's characteristics. In a top gate structure, the insulating or dielectric layer sits above the semiconducting layer, with the gate terminal on top of it. This structure has the advantage of making the OFET more resilient, as the insulating layer shields the semiconductor from the outside environment. In a bottom gate structure, on the other hand, the insulator sits on top of the substrate, but below the semiconducting layer. The gate terminal sits in the same plane as the insulating layer. This type of OFET is less resilient than a top gate OFET, but can be much more realistically produced. The high temperatures required to place the insulating layer onto the OFET can easily damage the semiconducting layer. This is especially evident in the case of OFETs, where their application as a biomolecule sensor often requires a semiconducting layer to be extremely thin. And then the material used for the semiconductor of our OFETs is called DPP-DTT. It is a synthetic polymer manufactured by Acilla. Due to the fact that DPP-DTT has a high molecular weight and is electron deficient, it has a high charge mobility. This makes it ideal for the use as a semiconductor in OFET. A high charge mobility means that it will react more quickly to the changes in its environment and thus provide higher quality data. It also allows for stable operation under non-ideal conditions. This allows for a longer life, and longer lives can have different applications to what they were before. And then there's also the dielectric bilayer, which provides an environmentally stable gate composed of Cy-top and HFO2.
So, to begin our experiments, we have a top-level diagram showing the flow of data through our components. The box on the left is the OFET arrays and the sensing component that are used in experiment 1. And on the right are the current reader, which is an INA 219 from Adafruit, a microprocessor, which is an Arduino, and an LCD screen display that are used to process the data from the OFET arrays and are used in experiment 2. Experiment 1 consists of the fabrication and testing of the stable OFET arrays. This is completed in a stable environment, demonstrating the change in current detected with water, pH 10 and pH 4 buffers. And the second experiment is reading a current across a 330 ohm resistor to test the capabilities of our current reader and its interface with the Arduinos and the LCD screen.
We had positive results from these two experiments. In experiment 1, we tested the reactivity of the OFET array in different pH solutions. It started by being immersed in water, which is neutral, and then when a buffer solution of pH 10 was added, the current went up from almost 0 to 2 nanoamps. Then, after a period of time, once it adjusted to this new environment, a pH 4 buffer solution was added, and the current dropped as expected. In addition, experiment 2, testing our physical device, the current, once hooked up to a 9-volt battery, the current through the 330 ohm resistor was measured to be 25.9 milliamps, which is within the expected range. This means that our device is capable of reading current correctly of different types of electrical components.
So as Luca mentioned, we are able to verify that the OFET array works in stable conditions, as well as create a circuit that is able to read the current sensor across a resistor. These experiments represent the different parts of the research, the fabrication, and the electrical part needed for the eventual sensor systems. The limitations in our results for this project are the effects of the intricacies of working with OFETs. These challenges include heat sensitivity, material availability, and small current values. Heat sensitivity and small size presented a challenge when making connections from the OFET. We could not simply solder on a wire at the source, drain, and gate. Instead, connections had to be made by extending a point of contact with silver paint, which then dried in the form of a thin conductive film. Then the wire was attached to the silver paint through alligator clips. Another limitation included material availability. The flexibility of the OFET was dependent upon the organic semiconductor. However, the manufacturer had previously supplied it was out of stock for the foreseeable future. We proceeded with the fabrication without flexibility, but the final sensor system needs to be flexible. As well, the current values that need to be detected by the sensor system are small. Most current sensors that are capable of reading such values are large and expensive. One solution to this is to amplify the current through an op-amp.
So for the future work of this project, the fabrication of a new set of OFET arrays on a flexible substrate needs to happen instead of our current glass substrate. This would allow for the OFETs to be able to be created into a wearable device with the reader and the display. After the arrays are on a flexible substrate, the two components from the previous experiments will be tested with an organic solution. And due to the issues of the current being too small to detect, future teams would add an op-amp to the existing circuit for amplification. The next step would be to streamline the device for wearability, so research must be done in order to optimize packaging of all the components together.